Hi everyone, hope you are doing well. I'm Reza, founder of the optimizationcity.com. In this video, we are talking about special cases in the Simplex method. So let's get started. In this section, we are uh, checking some special cases in Simplex method. First one, the picking the interim variable. There are some special case, so we speak in this uh, section. When multiple non-basic variables have the largest negative coefficient, this is the one of the special cases. In this case, we pick the one with the largest index. For example, in P1 model with the different objective function, we change the objective function by this. Both x1 and x2 have the coefficient of 3. We would pick x2 because it has the larger index. So the index of the x1 is 1, the index of x2 is 2, so we just pick x2. If we had picked x1 instead, we would have reached the optimal solution after the 3 iteration, whereas choosing x2 would have allowed us to reach the optimal solution with the only 2 iteration. The degeneracy occurs in the linear model when one basic variable takes on a value of the 0 in the basic feasible solution. This can cause cycling in the basic solution and slow down the simplex method, making it efficient in practice. So it's very important degeneracy in the practical. To get out the degeneracy, we can use the blend rules. These rules select a variable as an entering variable that has the lowest index and the lowest coefficient of the objective function. If there is a more than one choice for leaving variable from the basic variable, we select the variable that is closest to the objective function line or row 0. Unbounded. If none of the basic variable have leaving condition and the value of the entering variable can increase infinitely without any of the other basic variable become negative, the value of the z is unbounded. This situation occurs when the coefficient of the pivot column in the simplex table are negative, are non-positive, or negative or 0. To clarify this issue, consider the following model. Okay, the graphical representation of the above model is shown here. So you can see that the value of the objective function increased infinitely. The simplex table for this model is given here. And in the above table, we see that the x4 is equal to 12 plus 2x2 and x5 is equal to 18 plus 2x2 minus 3x1, where x2 can be increased infinitely. As a result, the value of the objective function increased to infinitely, and the constraints do not prevent the unboundedness of the objective function. If this happened, it could be due to the miscalculation or missing the any constraint. So here you can see that the pivot column behind the x2 is a negative or 0. So it showed that this model unbounded. If the problem has a more than one optimal solution, at least one of the non-basic variable will have the coefficient of the 0 in final row 0 in the simplex method. This means that increasing any such value will not change the value of the z. Therefore, we can identify the other optimal solution by performing the additional iteration of the simplex method, each time selecting a non-basic variable with the 0 coefficient as an entering basic variable. To illustrate this, consider the following model, and you can see the visual representation of the model above in picture here. The line between 2, 6 and 4, 3 has many points, and each one is the best one you can get. whenever which one you want, it doesn't matter. Since the mathematical model cannot consider the all economic factor in the real world, in this case you have many solutions, you may need an expert to help to choose one of them. So what happened in the simplex methods, in the simplex table, as you can see in the table here, two basic solutions for this table and for this table are the best solution with the optimal value of the z is equal to 18. You can see that the terminal condition for simplex method happened for this table and for this table. The fact that at least one of the non-basic variable has the coefficient of the zero. So in this table, you can see that the coefficient of the x3 as a non-basic variable is equal to 0, and the coefficient of the x4 in this variable as a non-basic variable is equal to 0. So it's when it happens, you have the multiple optimal solution. Whenever you have an inequality constraint, you can replace it with a pair of inequality constraint. However, this will increase the number of constraints, will not always convenient for solving the linear program. Instead, you can use artificial variable techniques, which we'll explain in the following example. Consider this example. The only change that occurs in the linear program model in this example is that the third constraint here become equality constraint. So the new model will look like this, and we can have the visual representation of the model here. So you can see that the feasible region is a line rather than the space. Unfortunately, this equation do not have an obvious initial basic feasible solution because there is no slack variable to use an initial basic variable for constraint 3 here. So you can see that you don't have any slack variable to pick as the initial to pick as the basic solution. So you need to find an initial basic solution to begin the simplex method. What we can do? Here, one way to overcome this difficulty. To get an initial basic feasible solution, you can create an artificial variable as x5 bar. You can do this by making two change in the original model. Add an artificial value, call it x5 bar to constraint 3 and make sure it's not negative. So it means it's non-negative constraint. So the new constraint will be here. And this model would be as a follow. And you can see that the third constraint has a basic variable. So what happened when you add an artificial variable x5 bar, it increased the feasible region, which is similar to figure below in the first model in the discourse. So surely it's completely different from this feasible region. The next step to penalize having the x5 bar is equal to 0 by modifying the objective function as here. So in order to make this feasible region to this feasible region, we should do following. So we have the objective function like this, where m represents a very large positive number. This method of ensure x5 bar in the optimal solution is known as the big M methods. It's very important in the simplex solving the model with the artificial variable. Before you can apply the simplex methods optimality test or find the entering basic variable, you need to make sure that all basic variables are eliminated from equation 0. However, the system of constraint is not yet in proper form because the basic variable x5 bar has a non-zero coefficient in row 0. So here, this is the basic variable, but it has a coefficient in the row 0. So to eliminate x5 bar from the row 0, you can subtract m times of row 3 and 2 subtract subtract m times of b from a. So it means in the other way, you times row b by minus m and sum with or add with row 0. By doing this, you have the new row 0. So the x5 bar has 0 in this row, which is the row of the objective function. By doing this, you can find the optimal solution for the original model by using the simplex method on the modify problem, starting with the initial basic solution this. So you do the following, the traditional way of the simplex method, and finally you can see that you have the optimal solution. X1 is equal to 2, x2 is equal to 6, and x3, x 4 and x5 bar as well is equal to 0, and the objective function is equal to 36. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by filling the contact form in our website, which is www.optimizationcity.com. Thank you so much and goodbye for now.